So, as can be expected for a summer course in which normally the sort of semester long 16 weeks of material is now condensed down into a mere eight, we are moving very, very straight along. Uh, Usually, we'll sort of do about 1 to 2 chapters worth a week. And this week in particular, now that we have a little bit of our fundamentals about how do we discuss sort of the nitty gritty details of measurement and sort of these more general tools of science, we really now dive down to very much trying to build our way up from as basic as we dare from the individual atom and trying to understand how those function, how we can predict their properties, and ultimately how we begin to assemble those atoms into compounds, making molecules, and ultimately then how those molecules then react with each other to do chemical reactions. So accordingly, we again are motivated in this course by this sort of idea that we as chemists and you by proxy inherit really this tradition from the alchemists of old, which to their credit tried very very hard, but were very much sort of misguided because they didn't quite have a grasp on how to do science properly and how to establish rules for themselves. While we probably don't want to repeat Henning Brand's experiment of boiling gallons of his own urine to try to become immortal, we do sort of want to build upon that tradition of trying to transform one thing into another and be able to predict what happens. Last week we talked a little bit about sort of trying to classify and how we describe what things are made of, what nomenclature or system of naming we as chemists use. From there, our roadmap is trying to determine how do we predict, how do we come up with rules for ourselves that allow us to predict whether something will be toxic or explosive, whether it will react or remain inert. A lot of that comes with trying to grasp the language of chemistry. Chemistry, like any other science, is very much a language with its own specific terms for things and the way we phrase things. And even if you're not going to become a chemist, if you become a biologist or some form of engineer, it's still helpful to be able to translate between the language of chemistry and whatever your other discipline might be. As a little bit of review of last week, we talked a lot about classifying the way chemists split up the material world. And when we look at these three different types of substances, diamond, dry ice, and crude oil, all of which are some form of carbon, we recognize that we are interested, of course, in zooming down to the atomic level to try to get as fundamental as we can. What are these things made of? If we zoomed in all the way down to the molecular level of a diamond, we would see this sort of crystalline lattice of a lot of repeating the same carbon atom. And that would look very different than looking at the dry ice, which seems to have two different types of particles clustered together. These three sort of form a cluster that moves around with each other. And of course, very different than this crude oil, which would have many different types of clusters of these atoms, now composed not just of one or two different things, but three or more, in different shapes, different arrangements. Properly, we break down the world between pure elements, things that only contain one of the element, one of these type of little hard particles, one of the 118, now in a much more updated periodic table. If we have several different types of elements combined together to form these little clusters, these molecules, we now recognize that as a compound whose properties are a lot more exotic, a little harder to predict, and we'll build our way up to there. We particularly notice, and we'll talk in depth today, that we always sort of have the same ratio of each of these things together. This molecule of carbon and two oxygen always exists as one carbon, two oxygen in the same sort of arrangement, this linear shape. Different shapes, different number of each implies a different compound with different properties. And then finally, of course, most of what we encounter in our real world is going to be mixtures of several compounds, whose properties, once again, are things we will continue to build up to be able to predict. Our discussion last week began, and we continue with looking at the bare unit of matter, this atom, derived from the Greek word to mean indivisible. And indeed, as far as we're concerned in this class, we don't really break this atom down into smaller components. That's a much more exotic brand of chemistry. But still, we encounter these pure elements consisting of just one element, both as individual atoms, individual particles. We also see them clustered together into these molecules, not quite a compound because we just have two of the same element, but still different than a single particle. And even pure elements like a sheet of aluminum foil exist as larger crystals. And so our task this week, and as we continue on, is again to try to figure out what are the rules that predict why some pure elements and later some compounds exist as individual particles versus molecules versus larger crystals. And of course, how do we more properly name them rather than just say particles, crystals, molecules? The confusing thing, and really truly thing, is that we're not yet equipped with rules to be able to tell the difference between helium, which exists as an individual single particle, not attached to anything, versus something like chlorine, Cl, with two particles, two atoms bonded together, attached together. And of course, aluminum, which exists as this large crystalline structure of billions upon billions of atoms, all clustered, bonded together. In order to figure that out, we really have to look under the hood a bit, try to understand what governs the interaction, not just of a single individual atom, but as they interact with each other. So peeking under the hood, potentially this is not something completely new. Potentially we've had a little bit of physics and or chemistry before, but this is as under the hood of our atom that we'll look at. Our atom, as far as we understand it, consists of really two regions of very, very different properties. The first one we talk about is the nucleus. That is the central little cluster of this atom. You may think of it as the sun in sort of the solar system of an atom. And this little cluster really is a very, very tiny fraction of the overall volume. The size of this cluster, sort of the diameter across, is about 10,000 times smaller than the overall size of the entire atom. Even though it's quite condensed and very, very small, this nucleus contains a lot of business. It contains protons, which are positively charged subatomic particles. These protons typically are very, very small in mass, many, many fractions of a gram. We usually round this value up to be a standard 1 AMU, standing for atomic mass unit. Biologists will often refer to this same mass as 1 Dalton, same thing, meaning the same measurement of mass. Within this nucleus, this proton really is what gives our atom its identity. Each of our 118 different elements in our periodic table with different properties have a different number of protons from 1 through 118. And we characterize the identity of this element as its atomic number, often represented by the letter Z for no particular reason, which is again just the number of protons, sort of the identity of this particular atom. Inside this nucleus, we also find the neutron, which is roughly the same mass as a proton, not exactly for quantum mechanical reasons, but as chemists, we generally round this once again to 1 AMU or 1 Dalton. Now, the neutron is neutrally charged, which really means it doesn't really interact with a lot of electrostatic forces, as we'll see in a moment. And we don't talk too much about the neutron in this version of the course, but we typically think that it's there sort of as a way to space out all these positively charged protons. All the positive charge clustered here in the center of our nucleus does repel each other, like repels like, and so it's thought a little bit that these neutrons help to space out that high density of positive charge. We typically refer to how heavy this particular atom is by calculating the mass number. Since a proton and a neutron both weigh 1 AMU, we typically just sum those two together and represent that by the letter A for the mass number, essentially the weight or mass of one of these atoms, depending on the number of protons and number of neutrons. Now, of course, for every positive charge that exists in the universe, we must have negative charges. And the majority of the volume of our atom is going to exist as what we call an electron cloud, a negatively charged particle that counterbalances our positively charged particle. These electrons are really the most mysterious bit of an atom, the bit where a lot of our classical physics begins to break down, and we need to start considering some quantum mechanical effects. But we can still say on a very, very basic level that these electrons are very, very tiny, roughly 1,000, 10,000 times smaller and lighter than our protons, and we typically round that down to be a mass of 0. So we typically consider electrons to be massless within rounding error. And really, the interplay, the attraction between the positively charged protons and the negatively charged electron cloud is really what is responsible for a lot of the chemical effects we see and a lot of the bonding and reactions that we will work our way towards predicting. Most of our work within this lecture is going to deal with neutrally charged atoms, so ones that contain an equal number of protons and negatively charged electrons. We'll talk more in a few slides. So this weird duality that we think of electrons as particles, things that we can count a certain number of negative charges, but that exist in sort of this diffuse electron cloud. We'll talk about that in a moment, but it is one of the weirder aspects of chemistry. Now, physicists will say a lot more about the structure within this particular atom, but we as chemists sort of take their conclusion and move forward with it. Really, I want you to have in your mind that a lot of chemistry is again governed just by basic physics and basic forces. And within this atom, there are really two main things we have to worry and concern ourselves about. The first is very obviously an electrostatic force. Quite sensibly and quite intuitively, that is the attraction between positively charged protons and negatively charged electrons, both within this molecule, but also between different molecules, the protons of one atom and the electrons of another atom. Just as we sort of look at magnets and other electrostatic forces, the further these charges are apart, the weaker that force is, the more potential energy is stored in that. Now, this electrostatic force is what we would classify as sort of a medium strength force. What that means is that it is not so strong that will never break it, that is thought of as a permanent force, but neither is it so weak that it doesn't really affect our chemical reactions. By stating a medium strength force, it means that it's sort of in the intermediate zone where most of our chemistry is involved and concerned with breaking and forming these types of electrostatic attractions. It's strong enough that they'll pull different atoms together, but weak enough that we can pull those atoms apart to rearrange them. That is, of course, different than what we call strong nuclear force. There is a force that does hold our nucleus together, the neutrally charged neutrons and the positively charged protons. And we note it here just so that you know there does exist a force that holds this nucleus together that's not positive and negative charges attracting. It is one of the four universal fundamental forces in the universe. We don't say too much about it because this is a very, very strong force, such that we at this level of chemistry typically don't concern ourselves with breaking and disrupting this force that holds our nucleus together. If and when you do get to the topic of nuclear chemistry, which does begin to mess around with this nucleus itself, changing the number of protons and neutrons, then we worry about the large force required to break apart these molecules, as well as large force that comes when forming new types of molecules, really responsible for the high energy nuclear reactions of fusion and fission. But we largely are going to concern ourselves with this electrostatic force, positive and negative charges attracting each other. Now, within chemistry, we've done a lot of work so far since a bunch of German monks many, many years ago to try to organize our 118 known, measured, observed elements into some sort of cohesive map type system. And because some of these names can typically get a little long, we usually abbreviate each of our 118 elements by some sort of elemental symbol. You probably have seen these before and use several of them in sort of common parlance. Typically, they are 1 to 2 letters long, paying attention to not just the letter involved, but also the case of the letter. All our elemental symbols begin with a single capital letter, and if there's any other secondary letter, those are always lowercase. So we would distinguish between something like cobalt, represented here by capital C, lowercase o, and many of the names do follow sort of the English name abbreviation. So cobalt, quite sensibly, is abbreviated as CO. Do be aware that that is maybe true for roughly half of our periodic table. Many of them come from more antiquated names. So like lead is named or abbreviated as PB for the Latin plumbum, which was what they originally referred to lead as, and AG for argent. Again, giving different symbols, sometimes related to their English name, sometimes not. Now, the periodic table is not something I need you to memorize. If this were 10 years ago, we would spend about a week trying to memorize the majority of the periodic table. But since everyone has a phone in their pocket and there's periodic tables wherever you look, this is not something that you need to memorize, but you should become familiar with over time. You'll eventually sort of become more familiar and have sort of a second instinct about what letter refers to what element, but this is something that you always want to be able to look up, always want to double check yourself. You don't want to think that you're working with one element when you're actually looking for another. Much of the confusion comes from the combination of uppercase and lowercase letters. If you are the type of person, and I'm guilty of this myself, who does not have great handwriting, or you do not typically distinguish between uppercase and lowercase letters, this requires you to do so. There is a big difference between writing a capital C lowercase o for the element of cobalt, a quite lovely blue metal, and writing a capital C and a capital O, which stands for carbon and oxygen and is the poisonous compound carbon monoxide. So do be very careful. Again, this standardized system of naming does require our handwriting to be a little neater and more distinguishable than maybe it normally has to be. Now, with our 118 elements on our periodic table, each of those represented by a different Z, meaning a different number of protons. So, of course, hydrogen with an atomic number of 1 means it has 1 proton. Helium with an atomic number of 2 means it has 2 protons, so on and so forth. All imply sort of a different element with different properties. But even within this 118, there are a few more variations in ways we represent different variants or versions of these 118 elements. In many cases, we often encounter these elements not as sort of their pure neutral form, but we instead encounter them as having undergone some sort of chemical change, which ultimately changes their properties. Next week, we'll sort of worry about how we predict when elements become one thing versus the other, but as a little bit of notation to get us started, we may often see these elements existing as ions. Elements, usually when we first sort of are born into the universe, have an equal number of protons and electrons, no net positive or negative charge. As they sort of travel through the world and they interact with others, they'll typically either gain or lose electrons. If they gain electrons, they'll carry a net negative charge. If they lose electrons, they'll carry a net positive charge. These ions, so-called, we represent by, of course, still implying with our elemental symbol, always starting with a capital letter, but we denote how many electrons were gained or lost, the overall charge, net charge of that particular element, by a superscript number and then a plus or minus sign to indicate how many electrons were gained or lost. Again, handwriting does count to make sure that you can distinguish between a normal case versus a superscript, a tiny little number to the upper right of your elemental symbol. Now, the last sort of variant that we'll talk about for this particular set of elements is the idea that every elemental symbol, a C for carbon, for example, represents a unique number of protons. Carbon, every single carbon atom in the universe always has 6 protons, 6p+, by definition. However, different atoms of carbon might contain a different number of neutrons. Some carbon atoms floating around this universe are going to contain 6 neutrons. 6 protons plus 6 neutrons gives us a mass number of 12, 6 plus 6. So some are floating around with a mass of 12 AMU, 12 atomic mass units. But if you looked a little further, you would see that some of our carbon atoms have 7 neutrons. 6 plus 7, of course, gives us a different mass number, a slightly heavier atom of mass number 13, AMU. Now, these atoms of carbon are all still carbon. The 6 positively charged protons all mean that they'll react more or less the same as each other, and our rules to predict how this carbon behaves really is mostly true whether it has 6 neutrons or 7 neutrons. But it's quite curious that there are some that are heavier than others. We call elements or atoms of the same element, both carbon, that have different number of neutrons and therefore different mass number, isotopes of that same element. Now these isotopes, depending on sort of how deeply you go into chemistry, is either a curiosity or something that will become your entire life. But these different mass numbers of different isotopes can be represented symbolically in different ways. We may either refer to this particular carbon-12 isotope, which contains 6 protons and 6 neutrons, either by writing carbon, or C-12. This dash number is the mass number, protons plus neutrons. We can also represent it more compactly with a little 12, the mass number, as a superscript before the letter. So up and to the left of our elemental symbol, different than the ionic charge, which is to the right of that symbol. Now, when we look at these different isotopes, we'll see that, again, every carbon that exists in this universe does react generally the same as far as we're concerned in this course. But we'll see that for reasons of mystery of the universe, that depending on the element, we have different natural abundances. And indeed, when we look at the universe as a whole, if we were to randomly pick a carbon atom out of the environment, we would probably get a random mixture of carbon-12, carbon-13, and some carbon-14. Now, after a lot of diligent work, chemists have been able to figure out that most carbon, 98.9% of the carbon atoms in the universe, are carbon-12, a very standard 6 protons and 6 neutrons. A very tiny fraction, 1.1%, are carbon-13, and even smaller, vanishingly small amount are this carbon-14. These different isotopes, again, generally react very similarly, but the fact that there is a small abundance and they have different masses allows us to do some interesting things with them. As far as we're concerned in this course, we typically will look at mixtures of these carbon isotopes, of which most are going to be mass number 12. And typically when we look at the mass of any random carbon atom, we're going to think about the atomic mass versus the mass number. Now the mass number again refers to a specific isotope, so carbon-12 has a mass number of 12, weighs exactly 12 AMU. But if you were to randomly pick 10 carbon atoms out of the universe, you get a mixture of all 3, and on average, you would be able to say that the average mass of your 10, 100,000 carbon atoms is going to be about 12.01. While the mass number refers to one particular isotope, we often in chemistry will use the atomic mass, which is a weighted average of all the different isotopes and their masses you can find. This weighting factor is the natural abundance, and the fact that carbon's natural abundance of one of its isotope is about 98-99% means that the average mass is still going to be very, very close to 12, slightly higher because of these higher mass isotopes. Most of your periodic tables, whether they're ones provided in your textbook, I have a couple of copies that versions I really like. Most of them are going to list 2 numbers. Some will list more information, but they will all guarantee list 2 numbers. The first thing every periodic table will list is the element's atomic number Z. Most of them will also list the atomic mass, in this case for carbon 12.01. Again, this average of all the isotopes as they occur out in nature. Mostly, when we look at our periodic table, we can tell something a little bit about the abundance of these isotopes. Again, for carbon, the fact that the average atomic mass is pretty much exactly very, very close to the mass of one of the isotopes gives us some hint that most carbon that exists in the universe is this carbon-12. The fact that is not all carbon-12 is where some applications of this corner of chemistry come into. We don't deal too much with isotopes within this course. It is a slightly more advanced topic in chemistry, but here is some preview and peek how you might use this, maybe as an environmental scientist, maybe as a nuclear engineer, maybe as a biochemist. Some ways we might use isotopes, and some ways in which they might matter. all sort of nuclear reactions, whether they are productive, such as the chemotherapy that helps kill cancer cells, uh, more productively, like nuclear power generation, or more destructively, we typically look at the radioactivity of singular isotopes. For uranium, which is sort of the big hot button, very popular radioactive element, not every radium that you find out in the world is going to be radioactive. Is going to undergo this nuclear fission reaction. In fact, really only one isotope, uranium, with a mass number of 235, is really radioactive. The rest of them are sort of slightly warm rocks, not typically dangerous, not typically productive for these reactions. And if you were to find a random chunk of uranium ore out in nature, you'd find that less than 1% of the uranium in that rock, in that crystal, is going to be this radioactive 235. So if you do find a chunk of yellow uranium oxide out in nature, you're probably okay. It's not going to immediately blow up in your hands because the natural abundance of this particular isotope is very low. If we want to use it for a application, to take advantage of the nuclear reaction that it undergoes. For nuclear reactors that would generate power and electricity, we typically enrich that ore. We sort of use centrifugation. We take advantage of the fact that these isotopes are different masses, and we enrich our sample to about 3 to 5% higher concentration of this radioactive isotope. Now, for nuclear power and things like that, we're typically only require a very small concentration of this radioactive isotope. If you want something more destructive, and the reason why the UN and the Atomic Energy Agency does track how much radioactive uranium is in any given sample, for something like a nuclear weapon or something more destructive, you require significantly higher concentrations, 20 to 85% of this particular isotope. Isotopes do, of course, come into radioactive and productive and destructive applications, but we also use it as a tool throughout biology, both human biology and throughout sort of environmental biology. We sort of very, very gradually realize that some of these isotopes, for example, some isotopes of carbon, because they're slightly heavier, slightly lighter than each other, are preferred by different processes. We find that plants in particular, who undergo photosynthesis, have an ever so slight preference, few fractions of a percent, 1 to 2 per mil. Plants ever so slightly prefer the lighter carbon-12 compared to the carbon-13 and carbon-14. These differences are very, very slight. If you just looked at a plant, you probably wouldn't be able to tell that it's ever so slightly lighter. But of course, within analytical chemistry, we can look very, very carefully with very, very good sig figs and high precision tools at very, very small differences in how much carbon-12 versus carbon-13 there is in a plant versus the air that you breathe versus the mineral you find in the ground. We've used this very, very slight difference in a plant's preference for the isotope of carbon to be able to convince at least the scientific community that most of the climate change we see, most of the CO2 that we are releasing does indeed come from petroleum-based sources. Over the last several hundred years, using ice core data, so little pockets of CO2 gas trapped in the ice from hundreds and hundreds of years ago, we're able to measure how much of carbon-13, the slightly heavier isotope, is there in the ice from decades and centuries past. And we see that all the way from about 1700 up to about 1950 or so, the amount of carbon-13 follows roughly the natural abundance. Plants sort of use them, breathe them out in the environment at a specific rate. But as we hit 1950 or so, and we start to burn more petrochemicals, more fossil fuels, which are all derived from plant biomass that has slightly less carbon-13, more of this carbon-12, we see that the CO2 in our recent modern air is very, very low in this carbon-13, has a lot more of the carbon-12. We've been able to show and conclude as a scientific community that this dip, this drop in the amount of carbon-13 comes from burning plants at an increasing the abnormal rate, reflecting that, or by burning all the carbon-12 enriched plant matter versus maybe older mineral sources, things in coral or fossils or other minerals. And so we can track very, very subtle differences informed by the difference in how biology treats these different isotopes to show where these different sources of chemicals are coming from. In this case, showing that CO2 is coming from carbon-12 that ever so slight, or sorry, coming from plants that ever so slightly prefers this lighter carbon-12. Another way that we've been able to look at this is to look at carbon-14. Carbon-14 is very, very low in abundance, quite rare, particularly because it is a radioactive isotope. And if you had a large amount of carbon-14, it would actually be quite dangerous. This carbon-14, by being radioactive, kind of gives us a way to judge how old the air is, since if carbon-14 sits around for too long, it'll decay into something else. So the presence of carbon-14 usually indicates relatively new air, recently created by respiration or other biological processes. And we can track the amount of carbon-14 throughout the air, and we typically see that older reservoirs, things like the deep ocean that has very old stored carbon, has low amounts of carbon-14, versus things that are relatively new, things that are more recent, like our upper atmosphere, have higher amounts of this radioactive carbon-14. Again, we've been able to track the differences in these isotopes, and we see that with our measured carbon-14, we see sort of a big spike and a big peak around 1960. This big spike and big peak comes from us testing nuclear weapons, testing atom bombs throughout the Cold War. And as we created more atom bombs and tested them and blew them up, we saw a large spike in this radioactive carbon-14. Conveniently, though, that's allowed us to be able to model and estimate. Of course, this big spike comes from blowing up a bomb. But because we're good at physics, we are able to subtract the effect of blowing up a bomb and radioactively decaying all that new radioactive carbon. And we've been able to see that over time, our carbon-14 concentration has been going down, suggesting that our carbon is coming from this deeper, older reserves from fossil fuels that don't have much of this radioactive carbon left over since they're millions of years old. And so there are different applications of these isotopes. Happy to point you in further directions if it's of interest. But we note it here to sort of show the importance and their application. But we typically don't do too much more with this unless you're particularly interested. Now we come back to sort of the main conceit and main thesis of our work. And this is really trying to, again, improve on the weird ramshambles of alchemy and try to come up with better rules to predict how these atoms behave and when they interact with each other. What makes them different from each other and how does that affect their properties? And ultimately, how do we predict what happens when we put two atoms next to each other? Do they remain separate? Do they connect together? And of course, making sure that we're naming things according to this chemistry language so we all are talking the same chemistry terms. Now, I will preface this section by saying that naming and describing elements, compounds, mixtures is terribly complicated and not typically very unified. Some of what we do in chemistry and how we name chemistry, the nomenclature of chemicals or the system of naming, some of it is via a systematic naming process. When I say systematic, it means that there are sort of interpretable rules. We represent the compound carbon monoxide, and we can sort of intuit that that means it consists of carbon and one oxygen. So a very systematic sort of translatable name. However, much of what we still work with, names like water or acetic acid, don't come from so systematic of a way of a naming system, but more historical, since we discovered these substances before we came up with chemistry. Still, to try to turn something that's ultimately very complex into something a little more tractable, we will work in this course to sort of translate between three of the most common ways in which we refer to a particular chemical and try to predict its properties. The first way that we're going to talk about today is talking about the chemical formula. This we treat as sort of an itemized list, a receipt of how many of each element are within a particular compound or molecule. We refer to this ratio of how many of each element as the stoichiometry or stoichiometric ratio. We'll say more about that in a moment. But we treat this list as sort of the barcode or definition of that molecule, in which different chemicals, different substances with different properties will have different chemical formulas. One thing to make note of, though, is that we can't only use the chemical formula as a way to describe a compound. Because these are three-dimensional particles with three-dimensional shapes, we could take the same number of each element and rearrange them in different three-dimensional structures, giving different properties. Different structures with the same chemical formula we typically call isomers, which we'll talk again more about in the coming weeks. But it's a handy way for us to begin to reference because it gives us an itemized list of what this compound contains, but is not the only way and not a unique way to refer to a chemical. Of course, we need to refer to these and commonly refer to them by a chemical name. Again, there are some systematic ways that we name things. Some of it, again, is going to be more historical. And much of this is going to become more confusing since chemists will refer to the same compound with several different names. A lot of chemistry, like learning any language, is sort of immersing yourself in that language and sort of practicing and learning things by example. Within this course, of course, I do allow you and I encourage you to utilize your resources, whether they are the internet, your textbook, other things like that, to help double check and help translate as we're working up our chemical fluency. Finally, the most definitive and unique way to refer to a chemical is the structure. Again, these are three-dimensional molecules that are arranged in a particular orientation. And ultimately, what is bonded to what, how they are arranged in three dimensions, really does tell us the most about their properties. We'll come to this next week, as it's a larger topic to deal with. But our endeavor is to try to be able to refer to a particular substance both by the formula, name, and structure, and translate from one to the other. It takes practice, and that's what a lot of this course is about practicing. But we'll begin here this week, primarily dealing with these first two, with the formula and the name. Now, as I said, this chemical formula is an itemized list, and you've probably seen some things before and have used them in other classes or more commonly. Again, this is a itemized list that lists all the elements found in a compound, as well as how much of each of those elements. There are some naming conventions, but strictly speaking, they are sort of more by practice, not by strict rules. Typically, we will list something that is a cation or a metal first, and so you will typically see the compound of sodium chloride, table salt, listed as NaCl. Again, referring to the elemental symbol of the two things in this compound, sodium and chlorine. You'll usually see as NaCl, but it's technically not wrong to write Cl and A, just a little odd, just a little strange. If there's more than one of each element, or a ratio other than 1 to 1, we usually write a subscript after the element. So this is a subscript on the lower line of our letter. And after the element indicates the number of each of those elements within this sort of itemized list. This set of numbers, which are usually whole integer numbers, gives us a ratio of how many of each element are found within a particular compound, whether it's a molecule or a larger crystal. While each of these molecules does list sort of an inventory of what's in the particular compound, there's a slight difference whether or not we're talking about a molecule, a sort of finite cluster of atoms, versus a larger crystal. At this point in the course, it's very hard to be able to predict which we have and which will be of which. We'll continue to build out those rules. But we'll lay out sort of this rule now and explore it in more depth. Some of these chemical formulas are going to be technically what we call molecular formulas, in which they list the total number of each element within that compound. You may be more familiar with things like water, which has the chemical formula or molecular formula H2O, which of course implies that one cluster of a water molecule, one little cluster of atoms, contains exactly 2 hydrogen, here shown in white, and 1 oxygen shown in red. The lovely thing about these molecular formulas and chemical formulas is that, again, it does indicate the identity of this particular compound. Every water molecule in the known world, in the known universe, has this exact same arrangement, same structure, and same ratio and number of each of these elements. So every water molecule you encounter is going to have the exact same chemical formula, exact same set of each element. If we look at something like a molecule of ethanol, which is the alcohol in a lot of sterilization equipment, as well as, of course, the one that you drink, this ethanol we might represent as a chemical or molecular formula as C2H6O. That implies that this molecule, this cluster of atoms, has 2 carbons, 6 hydrogens shown in white, and 1 oxygen shown in red. Now, with 9 different atoms, there's many ways you could rearrange these 9 different ones. So ethanol is not the only molecule with this formula C2H6O. There's other ways to arrange it into different isomers. And so writing the chemical formula C2H6O is not sufficient to refer to this particular molecule. We also, of course, need the chemical name ethanol. We may also, from time to time, write what we'll call a structural formula, which more so gives us a more expanded version of this formula that sort of writes out how these atoms are arranged and how this molecule is shaped. Because we see that this carbon is first bonded, attached to 3 hydrogens, followed by a carbon with 2 hydrogens, followed by an O and an H, we can often write this as CH3, CH2OH to sort of show the structure of this 3-dimensional molecule. It helps to clarify which particular version of a C2H6O we have, but again, we typically require all 3 ways, the name, the structure, and the formula, to refer to one specific molecule, ethanol, as opposed to something like diethyl ether, which is quite toxic. Now, this molecular formula, identical to all chemical formulas, we largely use for molecules discrete little clusters in which the subscripts refer to the actual total number of each of those elements. Just like some of our pure elements are existing as molecules and some exist as crystals, we may also have chemical formulas that are what we would call empirical formulas. These empirical formulas still underlie the same idea that the subscripts indicate the number, in this case the ratio of each of these elements, but recognizing that this does not serve one discrete little cluster of atoms, not one molecule, but usually a larger crystal. Empirical formulas, again, these numbers, these stoichiometries, indicating the ratio of each element, usually are for ionic compounds, which are composed of the ions previously mentioned. So when we look at something like sodium chloride with a chemical formula NaCl, we recognize, and we'll continue to learn more, that this particular empirical formula consists of ions sodium plus, chloride minus, or chlorine minus. And more importantly, that this chemical formula doesn't mean that one molecule of NaCl contains one of each, but rather a large crystal of NaCl contains Na and Cl in a 1-to-1 ratio. And if you were to take a little crystal of table salt and zoom in under a very powerful microscope, you would see again sort of this crystalline lattice of Na and Cl. And this particular chunk of sodium chloride, technically one big molecular cluster, will contain trillions of atoms of Na+. But because of this chemical formula, we know that this crystal must also contain exactly equal trillion atoms of the Cl-. Again, always existing in a 1-to-1 ratio, the total number of atoms might change depending on how large this chunk of material is. One characteristic of these empirical formulas is that they represent that every time we have positive charges, we need some negative charge to balance out. So as we will learn in the coming weeks, Uh, this empirical formula always balances the number of positive charges and negative charges. Sodium carries a +1 positive charge as a cation. Chloride carries a -1 negative charge as an anion, so it exists in a 1-to-1 ratio. For something like magnesium chloride, which you may use to salt your sidewalks, magnesium carries a +2 charge as a cation versus chloride's -1 charge. So these will pair in a 1-to-2 ratio to get balanced positive and negative charges. Naming. These ionic compounds, composed of ions, represented by empirical formulas that show the ratio within a crystal, are probably the easier portions to name in chemicals. These usually follow a more systematic, translatable naming system. Typically, we name these compounds by saying what the cation is, what the positively charged ion is, and then a modified name of the anion, the negatively charged ion. Usually, we modify the name by adding the IDE suffix to the name of the anion. And we usually don't have to represent the ratio of how many sodium to how many chlorine, for example, since we know their charge and know they combine in this 1-to-1 ratio. There's no uncertainty about that. So if we were to have something like sodium and chlorine, we would combine those together. Sodium, as we'll continue to learn, typically forms a positively charged cation, so we leave that name as is. And the chlorine, forming an anion, we modify with the IDE suffix. So sodium and chlorine become sodium chloride. By example, if we had barium, Ba, found there to the bottom left of our periodic table, barium combines with chlorine, positively charged barium, negatively charged chlorine, and we've named that barium chloride, again modifying the anion with the IDE suffix. For potassium and fluorine, they become potassium fluoride. For potassium and bromine, Br, they become potassium bromide. And for potassium and oxygen, potassium oxide, so on and so forth. Some difficulty comes when we deal with the middle part of our periodic table. This lower section here, which we'll say more about in a second, we typically call the transition metals, largely because they have this variable ionic charge. Sometimes a transition metal like iron can carry a +2 or +3 charge, having lost 3 or lost 2 electrons. In those cases, we have to refer to which cation of this iron we have. So rather than just say iron chloride, we'd have to say that this is iron with a +3 charge, which we represent by the Roman numeral 3. We may also use it by, again, sort of the more historical name, referring to this as ferric chloride. And that helps us distinguish it from an iron that carries a +2 charge as a cation, iron 2 chloride or ferrous chloride. Be very careful about these names. Again, the names tell you something about this compound, and the fact that it is ferric versus ferrous tells you something about the property of this iron. Some of our metals still are ones that we just have to apply the metal name, such as aluminum. Combining with oxygen becomes aluminum oxide. These things are things that we will sort of learn by example. And again, the purpose of this course is not to make you punishingly remember every triviality of chemical naming, but give you some literacy to know when you look up these names a little bit about what you're seeing and why iron and chlorine have slightly different names, implying slightly different compounds. Now, a lot of the compounds we look at in this level of chemistry are simply an atom that's a cation combined with an atom that's an anion. But sometimes we have a combination of a discrete atom that acts as a cation with a molecule, a combined cluster of different atoms that overall acts like a cation or an anion. If you were to zoom in on a very, very nice crystal of what we would call sodium bicarbonate, you would see that the chemical formula appropriately hints that there's 1 sodium, 1 hydrogen, to 1 carbon to 3 oxygens. Again, we see sort of this large crystal has a ratio of 1 to 1 to 1 to 3. When we interpret and when we look a little bit deeper and begin to parse apart how is this molecule or how is this crystal assembled, we would see that there is a sodium cation, Na+, just like the sodium chloride we've seen before, but this combination of HCO and HCO3 acts collectively as one molecule that overall has a negative charge. We typically call these clusters of atoms that form molecules that carry a charge as polyatomic anions. Since they move as a cluster, they move like a molecule of water or CO2 does, but has an overall ionic charge, in many cases negative, sometimes positive. We see that these polyatomic compounds are like our ionic compounds, empirical formulas telling us ratios, but we sort of recognize that instead of being composed of plus and minus atoms, they're composed of clusters acting as big cations or big anions. It's helpful to be able to break apart this cluster by still being individual Na plus balanced out by a cluster of HCO3, one hydrogen, one carbon, 3 oxygens, that again moves around and acts as sort of one big anion. Like any ionic compound with an empirical formula, these are repeating crystals, always with the same ratio of 1 sodium to one of these clusters of HCO3 minus. You also notice that because this hydrogen, carbon, and oxygen together defies sort of very simple naming convention, we've given this a unique name, again, a more historical name, usually referred to as the bicarbonate anion, the bicarbonate polyatomic anion. And overall, we refer to this overall compound, sodium bicarbonate, as more commonly baking soda. There's more polyatomic ions out there than just bicarbonate, nearly an endless number, in fact. And again, my task for you is not to memorize all these things, but to, again, have a little bit of literacy that if you look these things up, you'll have seen it once before and have a little idea what we're talking about. But things to pay attention to is that different names, again, imply different types of compounds, different properties. We distinguish between HCO3 minus, the bicarbonate anion, versus CO3 2 minus, carrying 2 negative charges as the carbonate anion. And there are many more, of course, beyond that. Hydroxides, different combinations of phosphorus, oxygen, and hydrogen, each with a unique name, a different chemical formula, and different properties. Some of these names are very, very similar, but again refer to different compounds. Nitrate refers to nitrogen with 3 oxygen. Nitrite refers to nitrogen with 2 oxygen. Our body responds very differently to these two substances, so it's important to distinguish between the two. Different combinations of sulfur and oxygen. Again, a different chemical formula, different ratio of these atoms implies a different compound, different name, so just be careful when looking and using these things. Chlorine and oxygen, as well as different combinations of carbon, hydrogen, and oxygen, which we'll talk about in the coming weeks. Again, this is not a list I require you to memorize, but at least know that if I see a name like chlorate that refers to something that acts like an ion, but requires me to look a little bit closer at what the chemical formula of this polyatomic anion might be. Now, we talked about how to name these empirical compounds, ionic compounds that combine cations and anions, things like sodium chloride. The rest of the world mostly comes in the form of molecular compounds. Sometimes we'll call them covalent compounds. These molecular compounds do have somewhat of a systematic naming system that is interpretable, is translatable. So we might be able to read into the Greek prefixes and distinguish between one carbon bonded to one oxygen as carbon monoxide, mono of course meaning one, and that being a different molecule, different properties than carbon dioxide, carbon with 2 oxygens. A small fraction of the molecular compounds follow these naming conventions. Technically, all of them do have some sort of systematic name, but more commonly, we might use a less systematic or more historical name. Very few people refer to water as dihydrogen monoxide, though that is technically the more systematic name. We, of course, refer to things more commonly, of course, as water. NH3 is what we refer to as ammonia, not relating anyone to what the chemical formula is telling you, just the name we've given it after many, many years of antiquity. Glucose has several names, the sugar we require for metabolism, depending on what type of chemist you are or whether you are a biologist. And again, this same molecule of ethanol has many different names, all referring to the same molecule, just different naming conventions, making our job a little more confusing. Again, this is not something I require you to memorize. This is something I require you to develop good research and lookup skills. Being able to Google things and find information reliably is an important skill as a scientist or engineer going forward. Some people have tried to make it a little more definitive, a little less confusing. And if you work particularly in industrial chemistry in a factory, if you work within engineering, as well as if you work within chemical health and safety or medical professions, you may often see chemicals referred to not by a chemical formula, which is confusing, not by a name, which is ambiguous, but by a CAS, Chemical Abstract Service Number. This is essentially a barcode, an ID number for every chemical, as well as some mixtures. And every molecule, every compound, as again, some mixtures, has a unique string of between 7 to about 12 digits long, referring much more authoritatively to a specific compound, using numbers rather than a more ambiguous name or chemical formula. Some of your problem set from this past week, as well as this going forward, has you looking into the safety data sheets of various compounds, and you'll see that the chemicals, for reasons of health and safety and to be unambiguous to first responders, refer to their chemicals within a cleaning product or a first aid product with this unambiguous CAS number. Again, this is not something that is worth your time and effort to memorize a lot of chemical names and formulas. You'll naturally start to develop a list, but make sure that you are getting good at your research skills. As a chemist, I rarely have memorized anything that I haven't learned just by using it over and over again, but there are better ways to look things up than others. I would say that things like random Googling, probably not as reliable as using a more authoritative source. Things like Wikipedia nowadays are pretty good. And if you would like some help finding better resources, I can definitely point you in one direction versus the other. Now, a lot of the chemistry we've been talking about has been very figurative, by which I mean we draw little cartoons of molecules and atoms on the screen, which is helpful to understand and envision what's going on at this molecular or atomic level. But ultimately, it doesn't help us do chemistry in the real world, it doesn't help us predict or measure things in the real world. We can count the number of hydrogen atoms and oxygen atoms on the screen and a picture that we've drawn, but we can't really count atoms in the real world, not with any tool we have available to us in a reasonable fashion. What we can do, and what you did yourselves in lab, was weigh a bunch of stuff. And we can often use math as a way to characterize and relate an imagined, envisioned atomic world to something we can actually hold, feel, and investigate. But to translate between counting the number of hydrogen and oxygen atoms in a molecule of water versus weighing the number of molecules within a glass of water requires some way to convert between counting things and weighing things. How could I, for example, if I had a beaker, a glass of clear liquid, tell whether or not that contained hydrogen peroxide, H2O2, quite a caustic oxidant, a disinfectant, but not something you'd want to drink, versus H2O, which of course you can drink without any problem. Obviously, we can look at these two chemical formulas and tell that the ratios are different. Hydrogen peroxide contains 2 hydrogen, 2 oxygen, versus water contains 2 hydrogen and just 1 oxygen. But how can we tell the difference other than counting atoms which we cannot see? Well, we could weigh them. We have scales, we can weigh things. And we could weigh, let's say we could weigh a single molecule of each of these potential compounds. If we could weigh a single molecule, we could add up the masses of all those hydrogens and all those oxygens. And the atomic mass of hydrogen is just about 1, reflecting that it has 1 proton. It's slightly above 1, 1.008, because a very, very small fraction of hydrogen atoms out in this world have 1 proton and 1 neutron, but most have a mass number of 1, an atomic mass of 1.008. So we can add up the mass of those 2 hydrogens plus the mass of 1 oxygen, and that molecule, if it was water, should weigh 18.02 atomic mass units for a single molecule. And we could distinguish that from hydrogen peroxide, which should weigh slightly more, 34.02 atomic mass units for those single molecules. If I could weigh those two and I could weigh what's in my cup, I could tell whether I have safe, clean water or toxic hydrogen peroxide. Of course, the difference between those two is really only 16 AMU, which is a very, very small mass. Again, an atomic mass unit is 10 to the minus 24 grams. And I personally do not have any scale that can measure so small of a difference of mass. There's really no scale we have available to us that's that accurate and that precise. So what can I do? Hopefully what we observed should have been the takeaway from last week's lab, is that measuring a single drop of water makes a very, very small change in mass, a very small change in volume, very hard to measure accurately and precisely. It was probably much easier, more precise, more accurate to measure a large amount of drops at the same time, 10 drops, 100 drops, giving a larger change, a larger difference, and a more accurate number, and a way to tell the difference between two different things. So rather than measure one molecule in time, we have to figure out how do we talk about measuring many, many, many molecules at the same time. If you've done chemistry at the high school level before, you may have come across the concept of moles. But if it's your first time hearing about it, it's quite an important way that we discuss large numbers of things in chemistry. A mole is what we refer to as a numeral grouping. In the same way that we might say that 12 donuts is the same thing as saying 1 dozen donuts, a mole is a way to group a large number of things into a much more compact unit. A mole stems from Avogadro's number, which is just this number that says 6.022, some more decimal points after that, times 10 to the 23. So it's a way to group 10 to the 23 things together, atoms, molecules, particles, electrons, whatever it is, into an equivalent mole of that stuff. Rather than saying, I'm going to measure 6.022 times 10 to the 23 molecules of water at once, I could say that amount of water is 1 mole of H2O. And for reasons that are somewhat annoying, the full name of the unit is mole, M-O-L-E, and the abbreviated unit is so conveniently MOL, saving us one whole letter in the process. And so rather than talk about measuring and studying individual molecules at a time, we can study with greater accuracy and greater precision billions upon billions of molecules at the same time, calling every set of 10 to the 23 molecules or atoms a mole of that substance. This allows us now to measure and to distinguish things not based on their atomic mass, the weight difference between individual molecules, individual atoms, but by their molar mass, the mass of 1 mole of a substance. In this class, I'll refer to these things as molar masses, but you may see different texts, other chemists, other scientists equivalently refer to it as formula weight, formula mass, or molecular weight, all referring to the same idea. How much does 1 mole of water weigh? We've picked this unit, and the reason why this number is sort of this random number is that conveniently, 1 atomic mass unit is equal to 1 gram per mole. So I have a hydrogen atom that weighs 1 AMU. 1 mole of that hydrogen atom weighs 1 gram. So instead of calculating the difference in their atomic masses, I can calculate the difference in their molar masses, looking at 1 mole's worth of water versus 1 mole's worth of hydrogen peroxide. Now the difference of about 16 grams is something I could definitely measure the difference of between hydrogen peroxide and water, allowing us to go from counting individual molecules, individual atoms, now measure something here at the bulk scale. This conversion factor is one we will use time and time again, something that relates counting the number of particles or molecules, a mole, to the measurable mass, which chemists and other scientists can do things much more easily with. This week lab on Wednesday, we're going to explore some of these conversion factors, again, trying to relate how do we go from something we can measure, like the mass of a substance, to counting the number of each element or the number of particles, and ultimately infer a chemical formula. So as not to wear ourselves down too quickly as we dive into this dense part of chemistry, we're going to take a break. We'll take a nice half-hour break to use the bathroom, just leave the building, eat a snack, whatever it is, and we'll come back at 10:30. Things to ponder as you do. So far, we've talked a lot about how do we name and describe different compounds. We've looked at sort of this systematic language, but we still don't know and can't predict. How do we know when things will form an individual atom versus a molecule versus a crystal? We don't have rules yet that tell us when to expect one versus the other. We know nothing about why sodium tends to form a cation, losing electrons, versus chlorine tends to form an anion, gaining electrons. And we don't really know whether or not we'll have one of these empirical formula ionic crystals versus a molecular formula. That, of course, is a big thing to build up to as we begin to talk about the details of how these atoms work and what governs their interactions. So we'll come back, because I've talked a little bit more now, we'll come back at 10:35, so take the good half hour to steel yourself against our first dive into quantum mechanics. So hopefully we've all watered and are steel ourselves for a little bit of quantum mechanics. So this is a general chemistry course. This is not physics. This is not an advanced chemistry course. This is not physical chemistry, but it is still helpful for us to discuss about what actually happens inside an atom. And for lack of any alternatives, it does require us to deal with the weird nature of how electrons are not quite particles. They exist kind of as waves. And there's different ways we need to talk about where we find electrons and how they behave. Protons are pretty easy to understand. They are tiny little particles that have a finite mass, size, and shape and move around like we would think a little billiard ball or ping pong ball. But electrons are a little weird. And my intent for this course is to give you a little bit of a quantitative understanding that helps us to predict when do different atoms interact and bond with each other without going too much into the weeds of the math, which gets very complicated. And I want to do so by analogy that helps to, in some cases, personify this atom. And I like to make the analogy of thinking of the atom as a city. This being Boston, we're going to think of it sort of like the city of Boston. So if you will entertain me, we're going to pretend that an atom, you can pick your favorite one, is going to be the city of Boston and its surrounding areas, and the electrons surrounding and living within the city are going to be the residents of the city of Boston, potentially yourselves. Now, with this city of Boston, there of course is a downtown area, and there's surrounding areas around it that get larger and larger, increasingly in radial distances from our city center. Every different atom, like different cities, has a different number of residents. And we can take a census, we can count the number of residents found within our city of Boston versus Springfield versus New York City, whatever it might be. Different cities have different number of residents, and we can count them. Ideally, everybody would love to live downtown. In theory, most people will tend to work downtown, will need to commute in there, so the closer you can be to downtown, the better, where all the cool stuff to do is. But there's only so much space downtown. It's quite crowded, and they haven't built tons of housing downtown, and it's very expensive. So quite necessarily, some people are going to live downtown. You're able to do so, but most people are going to need to expand out to the suburbs, to distances increasingly further and further away from our city center. Typically, As you move further and further away from downtown Boston, you get different types of houses, largely because there's more space. As you go further and further out, there's just physically more space around Boston than there is directly downtown. Generally, uh, downtown in Boston, you generally only find very, very tiny one-bedroom apartment studios, maybe, that can handle a few number of people. As you go further and further away from downtown, as you go further and further from the nucleus of our atom, you get different types of houses. One that have 3 bedrooms, townhouses. You even get sort of massive little mansions out there that have 5 bedrooms. More space means we can fit more people into the same house. Now, ideally, you try to live in downtown, as close to downtown as possible, because if you have to commute downtown, it's easier to live right there than it is to commute from JP or wherever it is you might be coming from. So, if possible, everyone's going to try to live as close to downtown as possible and fill these houses from our center, expanding outwards. So the first lucky people who arrive there first are going to pick the nice one-bedroom apartment downtown. The next two are going to come along. Now that downtown is all filled up, are going to go live in South Boston. Once we sort of get to these larger homes, there's now a little bit extra space. There's more space, not as many people clamoring for the same thing. And because now we don't have to completely fill up this particular 3-bedroom townhouse, these 4 people are going to space themselves out as much as possible. Like people, electrons don't like to double up if they don't have to, so everyone's going to try to pick their own room until the 4th person is forced to double up with hopefully someone that they like. Now, when we think of our electron, we really have to think of it exactly the same way as we would our city. In our center of our center of our atom, we have a very attractive downtown. Everybody wants to be as close as possible. But not everybody can live downtown. Not everybody can inhabit that small finite space. In the same way that we could map out where the houses are around in the greater Boston area, how many there are, how many people they can hold, and how far from our downtown city center is, we can similarly map out the same type of houses, places we might find electrons for any given atom, from something very, very close to our nucleus, close to this positive attractive force, all the way out to successively further and further distances from our nucleuses. We would call these houses, the places that our electrons could live, as subshells. And we typically fill out these subshells from the closest to our nucleus on outwards. Each of these subshells, whether it is a singular S subshell or a P subshell, will have different number of rooms, the same way that different houses structurally have different number of rooms. As far as electron houses are concerned, we have ones that contain 1 room, 3 rooms, 5, 7, and many more up beyond that. Now, in thinking of these electrons as people, we also have to be careful that we don't fall into the trap of thinking them too much as individual little particles. And I mentioned sort of the weird nature of quantum mechanics is that electrons do act as particles. We can count them. We can say that each electron has a -1 charge, but they also behave in more diffuse and uncertain terms. Electrons are like people in the respect that if you were to meet a person on the street, when you meet them, you could say exactly where they are, and you could say, you're right there, I can count 1 person. Electrons can be the same way. If you see an electron and you find it and you hold it and you touch it, you can say this is 1 electron with a -1 charge. But until you actually see and meet and find and position this person, you really can't say exactly where this person is. You can make some educated guesses. If you know something about this person, you may be able to guess probably where they are. If they're a student here, they're probably somewhere on campus. You may be able to say they're somewhere near a classroom that I know they have class on. You may be able to say that they're probably somewhere on transit, on public transit from here to their house. And you can make an educated guess on where I am most likely to find that person. But until I find that person, all I have is a guess or a probability of where that person might be found. I could, like you see in the picture here, sort of create a heat map, a probability density that says that this person is most likely to be found walking along this path than they are this path. That doesn't mean that this person is always going to be found here, but more often they're going to be found here than a alternative path through it. Electrons are weird in that they work more like uncertain people. We can see one electron and say this is one electron, has a -1 charge. But until we actually nail down a single electron, we generally have to talk about them as a probability of where they probably will be found, where they probably are located with respect to the nucleus around this central, within this atom. We have to sort of treat each of these houses, places where our electron might be found, like sort of a probability density of where these electrons might be, the same way that most people can probably be signed, or most people are probably found at home for many hours of the day, sleeping hopefully. So for electrons, we sort of pick these places as homes. Electrons are probably found, but not precisely in a weird quantum mechanical way. For the sake of this explanation, for the sake of moving through a description of how we think about bounding, we can kind of think of this in a more classical sense of this is the place that the electron lives. They're not always found there, but we can mostly guarantee and find that an electron is going to be living in one of these boxes, one of these rooms within these electron houses. Now, each of these boxes, each of these places an electron might be found, might be living, can be described by an address, just the same way that our homes are described by an address. And like addresses for people, the address of an electron has increasing levels of specificity, which tells us how close to downtown or to the nucleus they are. The first part of an electron's address is the shell number, represented by the so-called quantum number n. This is just an index number that tells sort of the most gross distance from the center of our atom, our nucleus. You can think of this as sort of describing the neighborhood in which our electron lives. Just as we can tell that if you live in Jamaica Plain, you're probably much further from downtown Boston than someone that lives in South Boston or Dorchester even. We can tell that an electron found in the 1, 2, 3, 4, so on and so forth shell number are increasingly further distances from our center atom. The electrons closest to our nucleus are going to be found in the 1 shell, one of these houses with a 1 in its address, versus something found in a 6 or 7 shell number are going to be much further away from the center of our atom, from our nucleus. We can refine where this electron lives to get a more precise definition and understanding of where we might find it, how it might behave. The second sort of part of this address will be the subshell. Sometimes we refer to it by the quantum number L. This subshell, again, tells us the type of house found within each of these neighborhoods. Shell tells us the neighborhood. The subshell tells us the type of house, whether it might be a 1-bedroom apartment, 3-bedroom townhouse, or a 5-bedroom little mansion. We have at least 4, theoretically more, types of houses that these electrons might be found in. Some of them are going to be 1-bedroom houses. Some will have 3, some will have 5, some will have 7, and theoretically more beyond that, though we've never observed it experimentally. Different types of shells have different numbers of subshells, and there's rules to predict why the first shell only has 1-bedroom apartments versus the second shell, n equals 2, has 1-bedroom apartments as well as 3-bedroom townhouses. The third has 5-bedroom houses, so on and so forth. But intuitively, we generally think that the further away you are from the nucleus, the more space there is. There's just more physical space that can hold larger houses that hold more electrons. Without diving too deeply into the quantum mechanics, we sort of take this as a result of this is the map of every atom's housing layout. These subshells have different shapes that we will use next week to begin to predict how these electrons interact with each other. But just as different houses have different configurations and shapes and structures, our different types of subshells, whether it is the S-type subshell with sort of 1 bedroom, our P-type subshell with 3 bedrooms, or D and F, so on and so forth, have different shapes. Our S subshells are these spherical shapes, radially symmetric. The P starts to adopt this very classic dumbbell shape with different lobes, sort of a positive and a negative half of this particular probability density, so on and so forth. Each of these subshells, S, P, D, and F, we can refer to the individual rooms found within that house as well. Some are trivial, such as our S subshell. Our 1-bedroom house really only has one type of orbital, one place these electrons might be found. But as we move further and further out and our houses get bigger, we start to have 3 rooms and 5 rooms. We can now refer to the individual rooms found within this house. Our P subshell, for example, which has this sort of weird dumbbell shape, has 3 rooms, and we refer to them as we refer to them individually as PX, PY, and PZ. Ways to number the fact that there are 3 different rooms with 3 different orientations. And we'll say more about those shapes next week. But each of these subshells, each of these rooms also specify that, like any reasonable bedroom, can only hold 2 electrons. These electrons are sort of doing reasonably well for themselves. They don't have to double up more than 2 people, 2 electrons per room. And it implicitly implies that our 1-bedroom S subshell can hold a maximum of 2 electrons in this location, versus our P subshell with 3 orbitals, 3 rooms, can hold 3 times 2, 6 electrons within this particular type of house. Again, going higher, moving further, more space, more electrons. The final sort of address, way that we might refer to where an electron is found and its characteristics, is by this property of spin. Spin is probably the thing we'll say least about in this course. It really is most important for more advanced topics in chemistry. But you may think of this as sort of the property of within your address, within the neighborhood you're found, within the type of house, and within the room that you live within your house. Spin is a property that has 2 values. An electron can either be spin up or spin down. It refers to sort of a magnetic moment of these electrons. We don't have to say too much more about that, but it gives us this property that says that each of these subshells, or each of these orbitals, can hold 2 electrons. Each of these electrons must have opposite spins. One way that they count to make sure there's only 2 of them there. And you may think of this by analogy as specifying within your bedroom, do you sleep on the left side of the bed or the right side of your bed? Now, obviously, if there are 2 electrons, if there are 2 people in your bedroom, you can't both sleep on the left side of the bed. You must pick different sides. But if you're the only person sleeping in that room, you may pick either the left or the right, and it doesn't quite matter as far as electrons or people are concerned. So every electron found within our atom has an address described by these 4 numbers, addresses that specify how far away from the center of our atom they are, how far from the nucleus they are found, as well as how many are found within the same house, the same distance, or same energy level for these electrons. Now, the beautiful thing about this map is that unlike real cities, every single atom has this exact same layout of houses for their electrons. Every single atom, every one of our 118 elements, always begins with a single 1-bedroom 1s orbital, followed by a single 1-bedroom 2s slightly further away from the center, then 3-bedroom 2p orbitals, so on and so forth. This order is the same for every single atom, every single element on our periodic table. The difference between our elements, one, of course, is that they have different number of protons, different strength of the positive attractive force pulling people towards the downtown center of this atom. Each of these elements, of course, have a different number of electrons, balancing out those positive protons, and so have to fill up these houses, these orbitals, to a different extent, depending on how many electrons they might have. For hydrogen, for example, hydrogen being found in the top left of our periodic table with an atomic number of 1 means that it has 1 proton, and for a neutral hydrogen atom, it means it has 1 electron. That one hydrogen atom wants to live as close to the nucleus as possible. So let's occupy half of this 1s orbital, either picking spin up or spin down. Again, doesn't quite matter, left or right of the bed. If we make an atom of helium, which is to the top right of our periodic table with 2 protons, those 2 electrons both want to try to live as close to the nucleus as possible at this lowest energy 1s orbital. And to save their commute time, they're going to pair up, 1 spin up, 1 spin down in this 1 orbital. As we move and we build larger and larger atoms with more and more protons and an increasingly larger number of electrons, they will fill out these houses, again, from the center, lowest energy, towards larger ones further away from our nucleus. These electrons, and ultimately the arrangement of these electrons, ultimately dictates how we begin to predict their chemical properties. The fact that hydrogen's 1 electron is found in a 1s orbital means this 1 electron will behave differently than fluorine's electron found in a 2p orbital. For now, we're going to concern ourselves with figuring out where they live, and next week we begin to figure out how to predict how they behave based on where they live. Unfortunately for atoms, we do a little bit of neighborhood profiling. Where they live kind of tells us what they are about, which is where that analogy ends with respect to people. But our job at this stage is to be able to figure out for any atom on our periodic table, for any element, where do each of its electrons live? And then from there, we'll begin to predict some properties. Again, the rules in which we fill up these orbitals is that we fill from the lowest, closest towards the nucleus, our 1s. We fill out as much as we can, trying to get as close as we can, but only being able to fit 2 electrons per orbital per each of these rooms. For any orbital, any room within the same subshell, so these 3 within the 2p, we'll call them degenerate orbitals, meaning that they all are found within the same house. They're all about the same distance from our nucleus, and so energetically, preference-wise, they're all about the same. So if we have multiple electrons going into a p orbital, such as for nitrogen with 3 electrons going into the 2p orbital, they will split themselves up, 1 per each room, before being forced to double up like oxygen has with this 4th 2p electron. There's a couple different ways in which we may refer to this structure. Here you see a much more exhaustive definition. But obviously, it's very hard to talk about individual elements with a very verbose notation like this. So we can talk about these addresses more conveniently by either referring to an orbital diagram. This is a visual depiction as shown here. We draw little boxes to show which orbitals there are, which are filled with electrons and how many. This gives us a visual indication of which orbitals have which electrons. But even this tells us is a little bit too much to put on a periodic table, at least a reasonably condensed one. And so quite often we'll abbreviate this, we'll condense this picture of where the electrons live down to an electron configuration. If you're of a certain age, you might think of this as a phone book, which sort of tries to reduce all these addresses down to a much more shortened list that really just gives the essentials. Ultimately, the way that chemists really think about this periodic table is as a map, quite physically, one that shows in 2 dimensions in a spatial orientation where do these electrons live, and in particular, where does the last electron to populate that atom can be found. We organize this based off of where those last electrons are found. We see that for something like hydrogen, with 1 electron that must live in the 1s orbital, we want to group it with all the other elements that also have their last electron that enters and lives in their city are also in some type of s orbital. Our theory is that everything that has an electron in an s orbital should react very similarly. So orbitals should react similarly to similar types of orbitals. We organize it based off of the columns, which we refer to as groups. Each column refers to a similar type of electron configuration, meaning their electrons are found in similar types of homes. We organize their rows based off their shell number, this n value, how far away they live from the center of the city, from the center of our atom. Things found here at the top of our periodic table with a low shell number, things like hydrogen, have electrons that can live very, very close to the center of their city, versus things found down here in the 7th period within a shell number of 7 have to live much further away from the center. So we can organize them based off of how many electrons they have and where those electrons are found. Now we're going to go through some examples and try to figure out how do we use this like a map to triangulate and figure out what is the electron configuration, what's the orientation of these electron addresses. Now you've probably seen many periodic tables, and certainly we usually use the ones such as we find here in our classroom, but technically that periodic table is not 100% correct. The real shape of the periodic table is this really wide beast that highlights sort of the arrangement of these different orbitals. For sake of compactness and fitting it on a nice 8.5 by 11 sheet of paper, we usually take this block of elements and we saw it off and sort of place it just down below, the same way that we do with Alaska and Hawaii on a normal map. We sort of rearrange it just for size and shape. But this is really the general shape of our periodic table, and it highlights a few things. It highlights that there is a set of elements, everything found in these first 2 columns, and which we refer to as the S block. The S block means that all of these electrons have their last electron, their final electron that they place somewhere in their city, atom as a city, is in some type of s orbital. The ones found here at the top, such as hydrogen, are placed in the 1s orbital. The row below in the second row, second period, is found in the 2s orbital, so on and so forth. Many other elements will have their last electron placed in a p orbital. So we group those together in a p block. Most of our chemistry we're going to talk about this semester deals with elements that have their last most reactive electron in an s or p element, or sorry, p block. And that's sort of the deal with most of our chemistry at this level. The elements found in the d block and the elements found in the f block are a little more exotic, a little harder to predict with the rules that we have for this course. We'll touch on them every once in a while, but we'll largely be leaving those for future, more advanced discussions of chemistry and their reactivity. Now, like Boston, an atom does have some places that you would rather live and some that you would not like to live as much. And most people are not going to be able to live downtown. And the further you are living from downtown, the closer you are actually living to just another town in general. It's always an interesting thing to figure out when do people stop saying that they come from Boston and start picking a different city that they identify with. And at some point, let's say if you live, let's pick a place that doesn't target anybody in particular. I would say that if you start to live somewhere out in Beverly, which is nice, very classic North Shore of Boston. If you live out in Beverly, you may be tempted to no longer say that you live in Boston, that you start to live on the North Shore, or identify your center as somewhere else. Atoms too are also, or atoms and their electrons are also kind of concerned with, at what point do I live so far from a city that I'm not really part of that city anymore, that I would rather go to some other city and be closer to some other downtown. Electrons, particularly the ones furthest from the nucleus, at these high shell numbers, far away from our nucleus, we typically call these electrons the valence electrons. They're really on the outskirts of our atom. Just like people who might live far from Boston may be more tempted to move to another city where they could live closer to that city's downtown, It's really these valence electrons that chemists spend most of our time worrying about, because these are the electrons that are most likely to leave our atom and want to move to a different atom where they could be closer to that atom's nucleus. And so most of our discussion is going to focus on a really small subset of our electrons. Ultimately, our periodic table can have up to 118 elements, 118 electrons, and it would be crazy to try to keep track of all 118 electrons and try to predict what they do. We're going to reduce it down to a much more reactive, much more flighty subset of electrons and try to understand their preferences and properties. So looking at our city as an atom, we can recognize that every atom is going to have some electrons that live very, very close to the center, close to our nucleus, close to downtown. These electrons are probably going to be less reactive, less likely to leave the atom because they live very close. They couldn't probably not get much closer to another city's downtown. We're not going to look at a lot of the properties of these core electrons that are less likely to leave, but we'll more so concern ourselves with the ones that live up here, further from our center, higher in energy, more likely to leave because they live so far away from the city center to begin with. And so through that lens of trying to keep track of these most reactive valence electrons, let's look at what our periodic table tells us about how to identify these valence electrons and understand their commonality. So I keep saying this, that the periodic table is ultimately a map, and just like a game of Battleship, the row and the column of a particular element tells me something about where these valence electrons are, what energy level they have, and ultimately how they will react with other atoms. Our periodic table, once again, is generally organized from left to right, top to bottom in increasing atomic number. So hydrogen with 1 proton, atomic number 1, is found here in the top left. Adding 1 proton gives us a helium atom, which is same row, same row, both filling the 1 shell. An electron in the 1s, also an electron in the 1s. As we add electrons, we move towards lower and lower rows. And every time we move to a different shell, from the first shell to the second shell to the third shell, we start a new row, we start a new period. So let's say we want to understand something about the element of magnesium. Ultimately, to understand what magnesium does, we have to understand what electrons do, how those influence its reactions and bonding. And I can claim, and I do indeed claim, that based off magnesium's position, I can tell what magnesium will react like and what other things will react similarly to magnesium. So you'll eventually learn by heart where magnesium is, but you would be able to figure out magnesium is found here in our second column, our second group, and our third row or third period. As the little box tells you, magnesium has an atomic number of 12, meaning it has 12 protons and 12 electrons to begin with. We typically call this either the second group or group 2A. Different tables will number it differently, but both refer to the same position. Now, this magnesium has 12 electrons. We don't need to know everything about all 12 electrons, but we need to figure out how many of these are these furthest most valence electrons, the most reactive ones. So where are these 12 electrons? I'll give you the punchline. Ultimately, this magnesium has 12 electrons, 2 in a 1s orbital, 2 in a 2s orbital, 6 in a 2p orbital, and the last 11th and 12th electron are in a 3s orbital. Now, different ways you could do that. You could refer to the map we had previously, but we can mark that by recognizing that everything found, the first 2 electrons fill up completely my shell 1s orbitals. The next 8 electrons will fill up my second shell, my 2 n equals 2 level, and my 11th and 12th electrons are going to be found here in an s-type orbital, since here we find it in this s block, these furthest left 2 columns. Now, based off the position, I can see that my first 10 electrons are going to be in shell 1 and shell 2. By being in shell 1 and shell 2, that means that they're relatively close to the center of this atom towards the nucleus, and they're held on strongly enough by the nucleus that they're not likely to want to leave their very cushy shell 1 and shell 2 positions. They don't want to move. They got it pretty good. But now there's a disparity. This last set of electrons, the 11th and 12th, now live one shell further, one neighborhood further away from the city center, and these last two electrons are more likely to want to leave and find greener pastures or a better place to live. We typically don't care about these first 10 electrons, who are not likely to leave magnesium, who are likely to stay there. But we want to track and figure out what the deal is with these last two electrons, who are most likely to leave magnesium. Because we only really care about these last two electrons and don't want to mess around too much with the first 10, we often write the electron configuration using the so-called noble gas notation. This far right column we call the noble gases for reasons that they are quite unreactive, and we'll say more about that next week, but allows us to abbreviate these first set of 10 unreactive electrons that are not going to leave our atom. This first set of electrons, 1s2, 2s2, and 2p6, has the exact same configuration as neon, which has exactly 10 electrons. It's quite happy to do so. So we typically write this expanded full electronic structure in an abbreviated noble gas notation to say that magnesium has all the same electrons as neon, full 1 shell and full 2 shell. Those are unreactive, typically not going to do anything, so we're going to group them together under this neon elemental symbol, square brackets, and call out just the most reactive valence electrons, these 2 electrons in the 3s orbital. Now, that's a lot of effort to go through for one element, and it would take forever if chemists had to sort of do that analysis every single time they wanted to talk about a new element. But one of the reasons why we organize the periodic table the way that we do is that based off of things that share the same row or share the same column, we can predict some of their similar properties. And here's one way we might do that. Let's say we want to predict something about calcium. How does calcium react? Where's the electrons? What does it tell me about its behavior? Calcium is found in the same group, the same column as magnesium, but one row lower. What that tells me is that for calcium with 20 protons and of course 20 electrons, that the first set of electrons are going to be very similar to how magnesium has grouped these core electrons as unreactive electrons. The full electronic structure for the first 18 electrons fills all of the 1 shell, all of the 2 shell, and all of the 3 shell. And what you're left with over is the last lingering 2 electrons, the 19th and 20th electrons here in a 4s shell. Very similar, very analogous to magnesium's situation with these sort of lingering 3s electrons. Now everything in chemistry is relative, and as far as calcium is concerned, the 1, 2, and 3 shells are very close to the calcium downtown as possible. So these first initial 18 electrons are not going to leave calcium. That's as close as they can get to a downtown, so they're going to stay associated with calcium and be fairly unreactive. For calcium, we care now about these most reactive valence 4s electrons. We would write this and express this idea of valence electrons, very reactive, very likely to leave, versus core electrons with, again, a noble gas notation that says that calcium's first 18 electrons is the same as one of our noble gases, argon. And we really care about the 19th and 20th electron here in a 4s orbital. The beauty of this is that every element in this column, whether it's beryllium, 1 above magnesium, strontium, 1 below calcium, so on and so forth, all of them are going to follow the same pattern. They're going to have a bunch of core electrons, but everything in this column are going to have 2 electrons in some sort of s-type orbital. And because they all have 2 electrons in an s-type orbital, we would predict that they would react very similarly. Those electrons are in the same type of house, will want to move for the same reasons. We typically refer sort of the general notation of this column by saying that all of these elements, magnesium, calcium, strontium, so on and so forth, have an ns2 generic configuration. They all have some sort of n shell, whether it's 1s2, 2s2, 3s2, 4s2, but all have 2 electrons in this s-type orbital and should react very similarly to each other. Let's try another group, another column, to see how this pattern holds. So let's talk about nitrogen, very important element for a lot of our muscle building metabolism. Nitrogen has an atomic number of 7, found here in our P block on the right side of our periodic table. We'll say that this is in the second period or second row in either the 15th or 5A group. Based off this position, we know that nitrogen's 7 electrons, the first 2 completely filled the first row, the first shell. The remaining 5 electrons, 2 of them go into the 2s orbital, and the last 3 go into the 2p orbital. Now, for this nitrogen, we now want to figure out what are the most reactive electrons of these, which ones we need to pay more careful attention to. And we recognize that everything in the 1 shell, the completely filled 1 level of this atom, core electrons not likely to leave. But everything that's in a partially filled shell, here we only filled out 5 of the 8 possible homes for an electron in the 2 shell, the second neighborhood. These 5 electrons we're going to treat as our valence electrons, and we'll write a noble gas notation that says the first 2 electrons, same configuration as helium, core electrons held tightly by the atom, not likely to leave. But the 3rd, 4th, 5th, 6th, and 7th electrons are now the most likely to leave nitrogen, most likely to react and do some sort of chemistry. We should be able to predict then that everything within this column, whether it's nitrogen or phosphorus or arsenic, should all have the same type of configuration, the same general pattern of where its last most reactive electrons are found. Oops. Oh no. Bring back my signal. One moment. We'll do the classic, if it doesn't work, unplug it and plug it back in. So we should predict that for everything found in this column, nitrogen or phosphorus, phosphorus should also have its last 5 electrons, 2 in an s orbital, 3 in a p orbital. Same thing for arsenic. The last electron should be in a 2 in an s orbital, 3 in a p orbital, so on and so forth. Antimony, again, follows this pattern, telling us where these most reactive electrons are, what type of house they live in, and eventually how they will react with other atoms. You'll notice that as we go further and down the periodic table, and we start to move out to orbits, neighborhoods of this atom that are much larger, that now include different types of houses, d orbitals and f orbitals that contain 10 and 14 electrons each, our reactive electrons start to become a little more tricky. We now have 4d10 electrons in antimony as our valence electrons. These, of course, are where a lot of our chemistry starts to become a little more exotic, where some of our rules have to become a little more nuanced. And we won't, in this particular course, go too much into those heavier, larger elements, and we'll spend our time mostly with these smaller ones whose properties are a little easier to predict at this point. But again, we notice this idea that everything in the same column has the same configuration, the same places that these electrons are found. Now that's true for everything in the same column, but we also have to figure out what does the row and the relative position of being the same row tell us about these different electrons, where they live, maybe how reactive they are. So I led off this section by saying that every element, all 118 on our periodic table, has the same set and the same order of orbitals. We see, regardless of whether it's magnesium or nitrogen, it's always 1s orbitals, then 2s, then 2p, 3s, 3p, so on and so forth. Always the same set in the same order. But it says nothing about the actual energy level, how strongly held those orbitals are to each of these atoms. If we go across a row, let's say we go from lithium there at atomic number 3 to beryllium with 4, boron with 5, carbon with 6, 7, so on and so forth. As we move across the row, what's true is that our atomic number gets higher. Every time we move one to the right within the same row, we add one more proton to that element. As we add more protons, we add more positive charges to our nucleus, our attractive force gets a little stronger. Stronger, more positive force means a stronger attractive pull on each of those electrons. And that means a couple of things about not just the order of these orbitals, but how far they are from the nucleus and what energy those might be. Intuitively, we should have some indication that because this is an electrostatic force, the stronger that force is, the more attraction there is between an electron and a nucleus with more protons, the closer those electrons are pulled towards the nucleus. So as we add more protons, those orbitals shift closer and closer to the city, towards the downtown. As we add more protons, the strength of that force is much stronger. This electron is held on much more strongly with more potential energy to this nucleus. As we add more protons, the other way we might say that is the pulling strength, which we might refer to as electronegativity, gets higher. Again, this is a good use of our intuition about electrostatic forces, positive and negative attracting. The more positive charge there is, the stronger it pulls, and the closer it holds on to each of these -1 charges for each electron. What that means for our elements is that as we move across the periodic table, as we move left to right, we increase the number of protons. Again, the types of orbitals are the same, the order of these orbitals are the same, but we fill with a different number of electrons, and these orbital energies begin to shift. If we start with something like carbon, found here in our second row, in our p block with atomic number 6, elemental symbol C, these 6 protons have a certain pull on the 1s orbital, the 2s, and the 2p orbital. These 6 electrons, 2 are placed close as they can be in the 1s orbital. The next 2 are placed as close as they can be in the next available 2s orbital. And the 5th and 6th electrons will split themselves up amongst the degenerate, equally distanced 2p orbitals. Now, let's say we add one more proton. We move one element across to nitrogen. Nitrogen now has 7 protons, slightly higher positive charge, slightly stronger pull on each of these electrons and the house in which they live. We see that it has the same set of electron orbitals, 1s, 2s, then 2p. We now fill one more electron because nitrogen has 7 electrons in which it needs to find houses for. But the slightly higher positive charge means that all these orbitals, all these houses are pulled a little closer to the nucleus. They're held a little more strongly by the nucleus, and everybody lives slightly closer at a lower energy level. And of course, this continues as we continue to add protons throughout our row. Of course, oxygen having the lower of these 3, 8 protons pulling on each electron as opposed to 7 as opposed to 6. What this begins to tell us is that each element not only has a different number of electrons, but a different relative order and the relative energy of each of these orbitals. While both carbon and oxygen both have 2p orbitals, if carbon was to give up one of its electrons and let it go live with an oxygen atom, that electron could live a little closer to a downtown at a little lower energy level. And we now begin to create some chemical difference. Why carbon is different than oxygen. Their relative houses, the available housing for each of the electrons, are at different distances and different levels of attraction between negative electron and positively charged protons. We observe sort of the same effect, a little bit of a modification of intuition within elements of the same group, again, same column. They all have the same general configuration, but of course fill to different shell level numbers. Here we show the valence electrons for N, 2 in the 2s, and then 3 in the 2p. Phosphorus, one element lower, same column, but one row, one period lower, also fills its last electrons, 2 in an s orbital, 3 in a p orbital. And in general, phosphorus having more protons 15 as opposed to 7 means all those orbitals get pulled slightly lower. But these shell numbers still sort of indicate a further distance from the nucleus. And so we generally see that the last valence electrons, as we go down a column or go down a group, still means that they're living further and further away from the center of the atom. More likely to leave a 3s orbital or 3p orbital from a phosphorus and want to move to something like a 2s or 2p orbital for a nitrogen. Again, every electron wants to live close to a downtown, a center of an atom, a positive charge. They don't necessarily care which atom they live close to. They'll make their decisions and react accordingly. And of course, finally, something arsenic, even higher, filling up to the 4th shell, but to the same 4s and 4p configuration. If you were to map this across all the periodic table, you see there a very nice general trend that as you add more protons, every orbital tends to go lower and lower in energy, more strongly attracted by these forces as you add more protons and increase atomic number. The same 2s orbital that appears in lithium and beryllium and boron and carbon and nitrogen and so on and so forth. Every time we add a proton, that orbital gets lower in energy, pulled more strongly towards the center of this atom, less likely to leave and being less reactive in general. At a very, very large scale, not just counting for the 1 and 2 and 3rd shell, all the way up to the 7th shell, we see this general downward trend that, again, matches their intuition. More protons, more attractive force, all these orbitals become lower, closer to the nucleus. Again, pointing out places in which our relatively simplified view begins to break down. As you get larger and larger atoms, more protons, more orbitals, we start to get weird sort of inversion and crossing regions, which is a topic that we leave typically for sort of a 3rd or 4th year chemistry course. Again, we sort of deal with this more cleanly behaved region in the 1, 2, and 3rd shell, where we see these general linear and downward decreasing trends hold true. Now, because the periodic table is laid out in a map showing increasing filling of these orbitals, more electrons filling to higher shell numbers, we have some general periodic trends that we can say are true about things found at the extremes of these periodic table. And it's helpful to help rationalize the things that we see, and it's also the way we begin to predict how different atoms will react based off of their relative position. If 2 atoms are on top of each other, what does that say about their sizes versus the energy required to move an electron? Our general periodic trends say that, as we saw previously, as we go left to right across the same row or same period, we add more protons. Those protons are pulling more strongly each of the electrons. Those orbitals shift closer to the nucleus. And we see this manifest itself as having smaller and smaller atoms as we continue to go from left to right. We might look at something like our 2nd row, comparing something like lithium, found here in the second period on the left side of our periodic table, versus something like fluorine, found in the same row, but on the right side of our periodic table. Because fluorine has 9 protons pulling on those electrons versus lithium only has 3, we expect that fluorine's atomic size, where those electrons are, should be much smaller, much more tighter. We also see that the energy increases, the energy required to remove those electrons increases. As again, we pull these orbitals, energy is lower, more strongly held and attached to the nucleus, more energy is required to remove those electrons. We often refer to that as the ionization energy, the energy required to remove an electron. We, of course, see similar trends as we saw on the previous slide about going top to bottom down our periodic table. Again, building the idea that as we add more protons, this attractive force pulls everything more closely together. But as we fill towards higher shells, our electrons have to live in neighborhoods further and further away from our city center. These two competing features gives us some of these main properties of the periodic table. That again tells us, based off where we find ourselves, whether we're in the top left, bottom right, so on and so forth of the periodic table, we can say something about the size of this atom, which tells us a little bit about how it behaves, as well as what energy those electrons are. How likely are they to leave our atom, engage in some sort of chemical reaction, maybe form a bond? Some caveats and some slight deviations to the otherwise clean, pristine rules. This is stuff that I tell you as a Chem 201 student, as opposed to when I teach Chem 120, which we gloss over a lot of details, is that our trend generally does hold. This ionization energy, the energy required to remove one of those electrons, take it away from the downtown that it wants to be in, generally does increase as you go left to right across the periodic table. Again, lithium, much easier to remove that electron with only 3 protons pulling on it than to remove the electron from neon with 10 protons pulling on that same type of electron. We generally see this trend, of course, that increases as you go left to right across the periodic table, but there are some weird notable exceptions. We see that there's a little bit of a hiccup, a little bit of a jagged inflection point here going from beryllium, Be, to boron. And again, one way that we know that our rules of quantum mechanics, that the colorful map that I've shown you about this set of orbitals is true, is that our experiments, our measured energy to remove an electron, matches up with what we would predict from this map. As you go from boron to beryllium, or beryllium to boron, you can consider how these electron orbitals are changing. Again, going from 3 protons to 4 to 5, I mean all these orbitals get pulled closer, get pulled lower. And so we expect that the ionization energy to remove this one electron from lithium will be slightly higher, will be slightly smaller than the energy required to remove this electron from beryllium that's held on a little more tightly because of the additional proton. It still holds true that boron pulls even more strongly, and so this 2s electron is even lower in energy, more energy required, higher ionization energy. But the most reactive electron within boron now exists in this 2p orbital, which is sort of one house away, one finite step away from the 2s, giving us this little inflection to an otherwise downward decreasing orbital energy and an increasing ionization energy, the energy required to remove these electrons. We also see a weird hiccup between oxygen and nitrogen to, again, this otherwise very nice monotonic trend. And we note that in the oxygen to nitrogen transition, going from nitrogen, which only has 3 electrons, versus oxygen with an extra 4th electron. This 4th electron that we remove from oxygen is this one electron that gets paired up with one of the other 3s. Now, like people, electrons don't want to share if they don't have to, because electrons will still repel each other. Electrons repel electrons, negative charges repel negative charges. So even though it is slightly lower in energy, this orbital, there's some value, there's some benefit to removing this paired electron, which means that oxygen's first ionization energy is a little lower just because it's getting rid of this uncomfortable sharing situation. So again, a lot of what we do and a lot of the things that we tell you about this type of quantum mechanical result is based a little bit on faith. It took many, many years of many very nerdy English and German people to come up with these sets of rules. But you should still have a little bit of skepticism of what I tell you. Some of it does seem fantastical, but I'm here to tell you, and I can help you find the appropriate sources to show that we do have experiments that verify these predictions, that verify this explanation of the order of orbitals that we see. It will unfortunately take until the very last lab of class for us to run our own experiments to verify these energy levels, but it takes a moment to build up to that. What is shown here, and typically what we talk about to refer to the energy level of a particular electron, is we refer to as the first ionization energy, the energy to remove 1, the last-most electron. But you can refer to the second ionization energy to remove 2 electrons, 3 electrons to their third ionization energy, so on and so forth. But we typically only talk about the first ionization energy in most of these descriptions. The final little few things and trends that we observe about this periodic table and how it helps us predict where these electrons are, how they will react and behave. We can also talk about how strongly any individual atom pulls on electrons. The ionization energy refers to how much energy it requires to remove an electron. Electron affinity refers to how strongly atoms will grab and steal electrons to themselves. Now, there's one slide on this because the trends for electron affinity are a little more tricky to rationalize. There's a little bit more going on that has to do with the quantum mechanical nature of these things. So I pointed here as just to illustrate the idea that there is something we can measure that shows how strongly an atom will pull on other electrons and try to steal them from other elements. What we'll be talking about more commonly and dive into in depth next week is the idea of electronegativity, which generally follows a very, very nice trend. These are unitless values. They're sort of just a number ranging from about 0.7 to 4 that ranks essentially how strongly an atom will try to steal electrons from other elements. It's a combination of several things. We note that the highest electronegativity, a value of 4.0, is found here in fluorine on the top right side of our periodic table. Fluorine has the highest electronegativity for a couple of reasons. One, it's found here on the right side of the periodic table. So relatively, within a given row, things on the right side of the periodic table have the most protons that pull most strongly on electrons, both within the atom itself, but also neighboring atoms. Fluorine, by being relatively high up in the periodic table, means it only fills up to the 2s orbital, or 2p orbital, and so it only has 9 electrons, filling up to a relatively short and close distance compared to something like astatine, found here at the bottom, but still on the right. Astatine now has 85 electrons that somehow mute the pulling power of those 85 protons, just again because they're located further out, and there's more negative charges offsetting the positive charges. But we again generally see a trend that based off the position of an element within the periodic table, we can tell something about how these elements treat and respond to their electrons, how strongly they hold on to the electrons, and by inference, how willing they are to give them up, versus how strong they're willing and able to steal or pull electrons from other atoms, engage in some sort of trade. Now, it'll take some time, take some practice, and our problem set 2 for this week, which is posted, does give us a few different ways to think about trying to relate the position of an atom or an element on the periodic table with some prediction about where those electrons are found and how reactive those electrons might be. We're building towards this intuition and trying to get a feel for how do we tell when an electron lives too far from the nucleus, that lives too far from the downtown. Most of chemistry is going to be dealing with when do electrons move, when do we break this sort of medium strength force between electron and proton, and allow it to be traded in between those. We are going to, of course, mostly focus on these valence electrons, the one found furthest out from our atomic nucleus, but we require a little bit more thought to think about how those actually compare one against the other. So, the intent and hope is that by the end of this week, we have a good instinct of how to describe individual atoms, where those electrons live, and sort of their relative energies and distance. We do so that next week we can begin to talk about how do we predict when electrons move, when they're traded between elements, when they're maybe shared between elements, giving us not just individual pure elements, but now compounds, molecules, and crystals. As a little bit of a sneak peek, the way we'll generally think about it, we're building towards, is that looking at an atom of sodium with a single 3s electron, reflecting the fact that it's found there in the first column of the s block, so 1 electron in the s orbital. This 3s electron is slightly higher in energy than the corresponding chlorine atom's electron. Chlorine is found in the same row, found in this third period, but on the far right side of the periodic table. by being on the far right side of the periodic table with now 17 protons as opposed to 11, all those same 3s and 3p orbitals are pulled lower in energy, more stable, much more strongly held by chlorine than sodium holds to those same houses, those same orbitals. These two atoms, neutral as they are, if they come in contact, they will try to figure out, could everybody be happier? Could there be a lower energy? Could all these electrons live closer to some sort of city center, some sort of nucleus, if they were to reshuffle their housing arrangement? Would they be happier if sodium gave up its one electron that's slightly further out than it needs to be, and had it pair up with the one empty spot here in chlorine, having sodium with a net positive charge, losing one electron, and chlorine with a net negative charge, having gained one electron, all those electrons being now lower in energy by simply reshuffling who lives with what. This movement and how electrons decide, quote unquote, decide to jump from one atom to the other is the basis for how we be able to predict bonding, whether two elements will react with each other to form some sort of cluster of atoms, or potentially not bond and leave, remain unreacted with each other. That requires us to sort of be relatively good with this description, drawing these orbitals, understanding the relative energy, being able to then visualize where these electrons would like to move within these cities. All right, luckily we'll end earlier than the 2 p.m. time we're allotted for. Some notes and reminders for this Wednesday. Obviously, this Wednesday we have another lab. This lab in particular, you'll want to make sure that you have safety goggles. You're welcome to borrow the ones there, but you've probably experienced that they're a little grimy, they're a little dirty, they're not terribly comfortable, and they look stupid. You want your own safety goggles, and particularly because we're going to be working with open flames, we're going to be heating and burning a bunch of stuff that gets very, very hot, and every once in a while cracks and explodes. So you want to make sure that your eyeballs are protected. Also make sure that because we have open flames, if you are a person with loose hair or garments, whether they're sleeves, necklaces, scarves, long, luscious hair, make sure you have a way to secure those because they will catch on fire. These things get very, very hot. Also for Wednesday, I will print out the worksheet, the lab report that you fill in with your data, but I would ask that you have a way to view the instructions, which will be updated later today. There are computers there, but they're a little hard to use, so bring a computer, bring a phone that you can read things off of. There is, of course, reading from the textbook that complements everything we talked about this week. This lecture covered chapters 2 and 3. You're responsible for what we present here in lecture. There is additional material. For example, the textbook goes into more details about the history of atomic theory, sort of incorrect theories we thought before we knew better. Certainly more mathematical details about quantum mechanics. If you're interested, I can help you navigate that. That's there for your own edification. You're only responsible for the things we present here in lecture. I will happily collect problem set 1 and lab report 1 on Wednesday. Happy to stay here afterwards to help with questions if you have those before you turn those in. And problem set 2 has been posted on Moodle covering this week's material and will be, of course, due a week from now, this following Monday. With that, we'll end here a little early. I will hang around if there are questions. Otherwise, I will see you all properly geared up for fire on Wednesday.